So welcome everyone. Today we have the pleasure to greet Dr. Nils Jansson to Ore Deposits Hub. Nils is a senior lecturer at Luleå Institute of Technology in Sweden, where he received his PhD in 2011 after completing a master's at Uppsala University. After his PhD, he worked for a few years with Boliden as an exploration geologist, continuing to expand the expertise that he gained at unraveling the histories of heavily deformed Proterozoic metal deposits. Nils is a principal researcher for the Vector project at Luleå, employing a holistic approach to mineral exploration of these ancient polymetallic deposits. These include VMS and skarn-style deposits that we'll learn about today. And in addition to spearheading this industry-sponsored research, Nils is also the project leader for the Explore student exchange program for master's students, which helps broaden the horizons for the next generation of exploration geologists from Luleå, Oulu, Freiberg, and AGH in Krakow. Today, Nils will teach us about the polymetallic deposits of the Bergslagen district and the complex processes involved in their formation and their reformation, and how to explore for such deposits in ancient terrains. Take it away, Nils.
So, just to check, can you see my screen now, my presentation?
Yeah, it looks perfect.
Okay, good. So, I should first apologize for probably having the longest title to date in the history of Ore Deposit Hub. But it's also a very long history that I'm trying to cover here. So it's actually two main, you could say, like legs that this presentation stand on. One is trying to say something about how we interpret the genesis of polymetallic sulfur deposits in the Bergslagen mining district of Sweden. Another thing I want to communicate is something about the way that we got to those conclusions. I mean, how we have actually been working with tackling these highly complex deposits. Before I will go into some of the details, I want to, of course, acknowledge some of my sponsors and people that I've been working with. So what I'm presenting today is actually like the aggregate of studies dating back to at least 2007 when I was doing my PhD project. And since then, I've been collaborating with a number of companies and geologists from basically all the mining companies exploring for sulfides in Sweden. That's like Boliden, Zinkgruvan, Lovisa-gruvan, but also I had support from the Swedish Mining Innovation and the Geological Survey of Sweden. And some specific acknowledgements I want to make today are the people listed below. Those 5 people, they have been like the key collaborators in the materials that I'm going to present today. In particular, Rodney Allen, who was the supervisor of my PhD project. So the main topic here that I'm going to talk about is metamorphosed ore deposits, because what I've been working with are metamorphosed deposits. These deposits, they have been heavily modified by metamorphism to the extent that we cannot really see what they were originally without trying to extract that information from the rocks. So why do we do that? I mean, if you want to, for example, revolutionize our understanding of VMS deposits, why don't you go to the modern seafloor where you can see the systems forming? Well, one of the things is that some of these deposits are actually world-class deposits. Like if you take this graph that I'm showing here, this is from Sangster 2020. This is a graph for SEDEX deposits or sedimentary zinc deposits. And what he's showing here is basically a comparison between Broken Hill type deposits and SEDEX deposits. And the Broken Hill type deposits, these are these heavily metamorphosed deposits that are so modified by these processes that there's a big amount of people that basically want to argue for that this is a specific deposit type, unlike SEDEX, unlike VMS. Whereas you have another school that is basically like Sangster saying that the reason why these look different is because they have been changed by metamorphism. So the takeaway here is that what we learn about in the textbooks, that's not necessarily what we will need to find the next big zinc lead silver deposits. So Broken Hill, for example, was the largest zinc lead silver deposit on this planet. Who knows how the next big zinc lead silver deposit will look like? Probably not like the ones that we teach about in the textbooks. So another thing is, of course, understanding the secular distribution of mineral deposits, because when you want to make a graph like this, like the one from Leach et al. 2010, this is showing now the secular distribution of SEDEX deposits. And the base case being made here is that these deposits, they started to appear in the Earth's record following the global oxygenation events. But you cannot really make this figure complete without inclusion of metamorphosed deposits. But by doing so, you are inducing a considerable amount of uncertainty into this diagram. And one case here that I want to highlight is the Zinkgruvan deposit that I've been working on. And in our project, we came to the conclusion that this deposit basically can be added to this graph in the sense that we can attribute ore formation to passage of oxidized brines and interaction with the redox trap. And you could say like a simple interpretation like this is basically pushing back this. So I mean, you may ask like, when did these systems really kick in? You know, when we had the GOE, but when did these systems kick in and started to form wall-class deposits? And to get this picture complete, we need to somehow find methods to unravel the complex ones, the complex deposits. Another motivation is, of course, completing the picture. And these three questions that I've listed here, well, I would say that the answer from my behalf is no. I mean, we already know this for banded iron formations, for example, and Komatiite hosted nickel deposits. That some deposits in the ancient records, we do not see the modern analogs. And when it comes to, for example, understanding the full range of sediment-hosted environments or VMS environments, then we have sometimes to go back to really old and complicated rocks and try to see through the effects of metamorphism. And we may, in that process, derive at models basically saying that these deposits, they were unique to start with. They're not just unique because they've been metamorphosed, they are unique environments, and then we need to try to understand them. And that's basically the opening for my talk today. I'm going to talk about the Bergslagen mining district in Sweden, which I would argue was one such unique environment. So starting with where we are, this is the Fennoscandian Shield up in Northern Europe. And what is being shown here are the major lithotectonic units in this part of the world. So the Fennoscandian Shield is what is shown here. And to the northwest, we have the Caledonide orogeny, which is over thrust. Then here we have the platformal cover of Europe. Looking into the Fennoscandian Shield, we have a Archean continental nucleus up here in the Kola Peninsula in northern Finland. And then when you move towards the southwest, you get into progressively younger rocks. And the orange here, this is the Sveco-Karelian orogeny, which formed between 2 to 1.8 billion years ago. And this is the part of the world I'm going to talk about today. And I'm going to focus on the Bergslagen lithotectonic unit, which is down here. This is a map of Sweden showing basically the same thing, but a more detailed picture of the different lithotectonic units. And this is just the BLU again. So skipping forward, this is a more detailed map of the BLU. And there's a lot of information on this slide. It's very heavy. So I'll point out the main features here. The brown units that you see here are granitoids and placed at around 1.89 to 1.87. And roughly 70% of the units in Bergslagen are granitoids of this age. These granitoids, they were placed into a succession of supercrustal rocks that are metavolcanic, shown here in yellow, and metasedimentary rocks, shown here in blue. And much in a similar fashion as you find, for example, in ancient greenstone belts, these supercrustal inliers are now floating around in a sea of granitoids. Another feature here are these orange and reds, and these are younger generations of granitoids. So even later in the history of this district, we had granitoid emplacement. So basically what we derive at here is that we had a picture where we had a supercrustal succession being built up. And then for a duration of around more than 100 million years, we had emplacement of various generations of granitoids, which currently dominate this district completely. So this is a magmatic province. If you look on the distribution of mineral deposits, which are shown here in blue and red, the blue are iron oxide deposits, and the red dots, they are sulfide deposits. You can clearly see that there is a spatial affinity of these two, the metavolcanic inliers, shown here in yellow. Not as much in the metasedimentary inliers and not as much in the intrusive rocks. So already this is telling us something in that the most prolific phase in mineralization here was in conjunction with this major volcanic cycle, which is like one of the earliest components we see of Bergslagen. So the figures I'm showing you here is from a new book by Mike Stevens. Mike Stevens, he basically divided the history of Bergslagen into 3 tectonic cycles. And this is what is being shown here to the right. So in Mike's model, Mike basically envisioned a cycle starting with extension and building up of this volcanic succession, followed by intrusion, and then completing with a cycle of deformation, ductile deformation, and regional metamorphism. And this occurred actually 3 times. So we have 3 tectonic cycles going from extension or transtension to compression. So what this means is that all the mineral deposits that we have in here have seen at least two of these cycles. And this is the main reason why these deposits are so difficult to work with. So if you make a comparison, this is now showing a structural map. What is being shown here in different shades of yellow are the metamorphic domains. So the darker yellows here, they are amphibolite to granulite facies domains. So these rocks have been metamorphosed at least once to amphibolite facies. Whereas in the center, we mainly have amphibolite facies and locally some green schist facies domains. What this means is that if you want to go and tackle this district by using like conventional geochronological methods, you will find some problems in the sense that most of the geochronometers that you can apply, for example, argon, will tell you actually about the cooling history of the Svetkokoryllian origin. And as I just showed you, this is not when the ore deposits were forming, they were forming earlier. So to cut it short, it's very easy to go here, sample something and getting an age. You will always get an age from a sample. But then getting a meaningful age, that can be more tricky. And when it comes to dating like the early events, then we basically, the only real robust system that we have to work with is uranium, lead, and zircon. And for this reason, we have to put more emphasis, for example, on dating cross-cutting units than on dating, for example, biotite in the alteration zones, because this may be reset and giving us a considerably younger age. This is just to give you a taste about how the rocks may look like. This is from the so-called northern structural domain. So this used to be a granite, but now it's actually a mylonite. And you can still see some of these feldspar crystals that have now turned into augens. But all of the other minerals have been smeared out into this mylonitic foliation. We also have this intense stretching lineation, which is not just in the northern part of the district, but also regionally. And so all of the rocks are basically stretched out into rods. So when we look at these rocks, we have to take into consideration also on which orientation we are looking at them from, because they may look very different from different sides. These are some other rocks. This is actually from the central part of the districts when we have not as much shearing, but we still have considerable amount of deformation. So this is now garnet porphyroblastic migmatitic pelitic rock. And so the banding that we see here is not primary. This is actually the foliations. And up here we have at least 2 different generations of foliations. And generally, everywhere we go, we have to deal with at least 2 deformation phases. So what about the mineral deposits? Well, they are of course also affected by this. This is showing the stratiform zinc-lead silver ore from the Zinkgruvan deposit. And this is a rock slice showing the effects of having at least 3 deformation phases in the Zinkgruvan area, where we have the original banding in this ore has been now folded into these domes and basins in this particular sample. If you make a thin section here, you'll find like this foam texture. Everything has been granuloblastically recrystallized. So you don't even see like the original grain boundaries. Actually, you will even struggle to see the banding in this ore in the thin section because of the coarsening. And you can imagine what kind of limitations this yield for doing like microanalytical methods. And fluid inclusions, for example, you can forget about. And this is now the Garpenberg deposit, or the Lappberg ore body, where we have stretching, and like this ones we saw around the shear zone. And basically, this ore body goes from 400 meter depth to 1,600 meter depth at least, and it has this rod-shaped geometry just because of stretching. And you can see that the metal zonation in this deposit has been transposed during the deformation. So the deposits, they are folded, shear, stretched, and basically always to some extent modified by metamorphic recrystallization. But nevertheless, we can actually go to these areas where we find relic textures in the rocks, and that's basically our main approach here, is that we stay away from these heavily deformed rocks, and instead we look for these Rosetta Stone kind of geological localities. We can actually extract information about the primary depositional environments and processes, such as here. And here I have to give credit actually to the Aussie. So in particular, Rodney Allen, who was my supervisor for my PhD project, he basically revolutionized the way that we deal with these kind of rocks in Sweden. So what he did was that he systematically revisited many of these localities where we had well-preserved rocks, and he synthesized this into you could say like a geological model for Bergslagen, basically trying to recreate the original depositional environment. And what is shown on this picture, for example, here we have cross-bedded quartzites that underlie the volcanic succession. They're highly important in the sense that they tell us that the volcanic succession must have been deposited on top of relatively shallow marine or even fluvial siliciclastic sediments. So this was not a deep marine environment. The volcanic succession was actually built on relatively shallow rocks. Another thing is that we find limestone interbeds or marble interbeds in the volcanic succession, and we have beautiful evidence of stromatolites in some areas, which is also telling us that the volcanism was mainly shallow marine in character, and that whenever we had pauses in volcanism, we were forming bionic carbonates, not pelites, as you find in many VMS districts. So these two together they are highly indicative of that we were in a shallow marine environment for much of the geological evolution in Bergslagen. Third feature was that many of the volcanic rocks are really thick successions of pumiceous rhyolitic rocks. So in some areas we can still find the original pumice fragments occurring as fiamme, but they lack the evidence of welding that you would expect in subaerial conditions. So altogether, these pumiceous deposits are also consistent with a shallow marine environment, mainly involving phreatomagmatic volcanic activity. So the outcome of a work that was done in the 90s by Rodney Allen and people from companies and surveyed was this model for the palaeoenvironment in Bergslagen, which basically envisaged Bergslagen as a backout basin or intra-arc basin, which was built on extended continental crust. And many of these pumiceous units that I showed a picture of, they could be shown to be several hundred meters thick, which means that they must have formed in huge depressions. Now, the interesting thing about this is that they may be overlain and underlain by stromatolitic carbonates. And if you take into account the photic zone for bionic growth being 200 meters, it means that we must have had extension to generate accommodation space for these thick pumiceous units. And the easiest way to envisage this is by having Bergslagen basically being composed of a series of nested caldera volcanoes. Besides stromatolites, we also have banded iron formations, and also other hydrothermal precipitates are formed during pauses in volcanism. One of the things that is actually rare in Bergslagen is shales. So when we find pelitic rocks, it's mainly deep below the volcanic succession or on top of it. Now, this volcanic succession can be shown to be up to 10 kilometers thick in some areas, with repeated evidence at several different stratigraphic levels for shallow marine environments. And there's no major unconformity here either. So if you add this together, what we get derived at is a picture of an environment that's undergoing heavy extension, basically keeping pace with infilling of the basin by volcanoclastic debris. When it comes to the sulfide deposit, it was shown that we have two principal types. The first type are these called Schwarz type deposits, which are stratabound deposits that replace limestone associated with skarn. And the other type was stratiform deposits that occur as sheets in the upper part of the volcanic succession. And these are the ones that I'm going to talk about today. So, I mean, the opening point for much of what I did during my PhD and subsequently have been to try to develop this model further by trying to understand the relationship between these two deposit types, and also understand the relationship between deposits forming on or close to the seafloor to deposits forming in a much deeper environment proximal to intrusions. And why is this relevant? Well, I don't know if you know this, but Bergslagen is the type locality of skarns. This is actually where the word skarn was first coined by, not by Alfred Elis Törnebom, Turneboom was the guy who adopted this into the geological nomenclature. This term is even older. It was used for by the mine workers for gang rocks around the ores. And actually, the word skarn is actually, it means something like prostitute or trash. So basically, this was the bad trashy rock that you would find before you entered sulfide ore. So imagine you're mining your way through a soft marble unit, and then you get into this bam, like amphibolite, garnet, quartz. I mean, you could have like garnet, pyroxene skarn, which is really heavy and all that. So you can probably imagine the mine workers were cursing when they stumbled upon these skarn zones, but they knew that they were close to mineralization. So we have a lot of skarn in Bergslagen, and it has always been the question here, did these skarns form with the mineralization, or did the skarns form when the mineralizations were metamorphosed? Because you can form skarn just by metamorphosing rocks that have the right composition. I will get back to that later. But this is the main conundrum that has been associated with this Svalst type deposits. If I summarize the key features here, the upper 5 features here, I mean, most people would say that these are very much VMS-like, nothing weird about them. Massive sulfides in a seafloor setting, they are semi-volcanic. You have stringer zones along below the mineralization. You have rocks where the feldspars have been destroyed, replaced by chlorite, cerussite, etc. And when you do find minerals like garnet, etc., they have grown as porphyroblasts. And anywhere where you have metamorphosed VMS deposits, you get porphyroblast growth in the alteration zones. So if you only look at that, you can easily argue that these are some kind of unusual VMS deposits formed in a shallow marine environment. But the key thing here, which differs, is that when you get into the ore zone, we can see that these have replaced limestone interbeds in the succession. They are not exhaled on the seafloor. Mainly, they have been replacing carbonate units below the seafloor. And the gangue mineralogy is commonly rich in calc-silicates like garnet, pyroxene, etc. So starting from the top here, we say summarizing the main features of the Svalst type deposits. We always have a seafloor component to these systems. So it varies a bit in character. In some places we have these banded iron formations, like this one, for example, rich in hematite. And here you can see some of the regional metamorphic calc-silicates. Like we have these thin bands that contain garnet, epidote, amphiboles, etc. And if you read papers by, for example, Klein, 1973, there's nothing weird about these calc-silicates. These are what you can form just by metamorphosing an iron formation. Here, for example, we have tremolite, antophyllite, chlorite bands interbedded with magnetite. In some areas, we even find laminated sulfides associated with these rocks. So in this deposit here, we have laminated sulfides, and here you see these garnet porphyroblasts. Well, if you look here, this is a more silty part, and then if you move upwards, you get into more porphyroblastic material, and this is something that you can interpret as a relict normal grading. So this is basically an increasing amount of clay, which led to better conditions for forming porphyroblasts during metamorphism. This is another example. So typically, you will find that many of these Svalst type deposits, they have exhalative phases nearby. And if you sample these and have a look at them, they are not really that different from the, for example, the exhalites that Sean McClenaghan was talking about a few weeks ago. This is the iron formation that I was showing you right here. It has this beautiful positive europium anomaly. You can find cerium anomalies. If you go into details and looking at the geochemistry, comparing proximal and distal iron formations, you can use the same tools in Bergslagen as you can use in Bathurst, for example, from vectoring from distal to proximal. And you can apply the same model to how these were forming. You basically had a hydrothermal plume, then you had fallout. The europium anomalies you can, for example, explain by precipitation of iron oxides and then scavenging of rare earths from the hydrothermal fluid and from seawater. So, and also you can plot the samples on this Boström plot, which is basically designed for understanding hydrothermal precipitates on the seafloor. So these are much like any kind of Tuffaceous exhalites that you will find in any VMS district. So far we have not really seen anything unusual about these deposits. If we move down and look a little bit more in the subseafloor components, this is where we start to see some evidence of this carbonate replacement. So like this is the Stolberg unit, the Stolberg deposit, which is another part of Bergslagen. And here we actually have sulfide deposits replacing a marble unit, which is an interbed in this volcanic succession. Now, when you have this kind of replacement, you may always discuss, is this an epigenetic deposit replacing the carbonate, or is it rather something that occurred just below the seafloor? Well, in this case, it's critical to integrate any kind of studies of alteration with stratigraphic analysis. Because what we can see here is that there's an asymmetry in the alteration zone that occur adjacent to Stolberg. So if you go on the west side, which is a stratigraphic hanging wall, we basically have no alteration whatsoever. Whereas if we go on the right side in this diagram, where we have the stratigraphic footwall, then we have this really thick, actually several hundred meters thick alteration zone, in which we have considerable modification of the original alkali contents, for example, and we also have basically destruction of all the feldspars that we had in the rocks originally. So this kind of asymmetry that we see repeatedly around these false type deposits is something that's very difficult to explain from a epigenetic standpoint. Whereas if you take it to like a syngenetic standpoint, it's really simple in the sense that the easiest way to explain this is that basically when this alteration happened, these rocks had not been deposited yet. So this is basically the post-hydrothermal rocks depositing on top of this deposit after it had formed. So, and this is something that we can also use as evidence for that this deposit was forming on the seafloor or just beneath it. And this is just not on a local scale. This is the profile I was just showing you. But this alteration zone that we have stumbled upon there, we can actually trace for several kilometers. So this asymmetry comes back also on this scale. So further east of the Stolberg mining field that we can see here, we have several kilometers actually of sodic enriched rocks. When we get closer to mineralization, we get extreme potassium enrichment. And then when we get into the mineralized zone, we have extreme iron and manganese enrichment. And then as soon as we step left the Stolberg, we get into basically unaltered volcanic rocks. So, and this is a typical feature that you find around many VMS deposits. Alan Galley called this regional scale deep semi-conformal altered zones. And he basically made the case that these are regional scale convection zones that basically represent you could say like where you produce the modified seawater fluids that produce VMS deposits. And this is actually where most of the metal stripping is going on. So, and we actually have the same kind of zonations here, for example, with shallow potassium enrichment and deeper sodium enrichment that we see. Alan Galley actually used some example from Bergslagen when he devised this model. So it's not really a foreign concept, actually it was partly derived from here. So, so up to that point, we can basically see that we can think of this deposit as some kind of seafloor deposits. That, but the complexity that we have in them is that when we start to look into detail in the alteration zones, then we will find that the mineralogy has been completely replaced by new minerals that are formed during the metamorphic growth. And this is where it's critical to integrate structural analysis, because when it comes to these rocks, for example, we can show that many of the minerals that we see here, they grew in rocks that were already altered. So for example, here in the deeper sodic part, we have gedrite porphyroblasts. So this alteration zone, it's folded, it's stretched, but the gedrite porphyroblasts, they are not defining any fabric whatsoever, which means that they must have been forming after this deformation events. The same here goes for these garnet porphyroblasts that we find more proximal to mineralization. They overgrow an earlier S1 foliation and they are affected by a second S2 foliation. So these kind of relationships we can explain by basically saying that we had rocks that had been altered and we metamorphosed them. The important thing here is that if you go map these, people tend to call this garnet alteration or gedrite alteration, but it's not strictly speaking alteration. This is metamorphosed alteration. And why it's important is that if you go to an area where you have green schist condition, you may have exactly the same conditions, exactly the same alteration, but you will not find the same minerals. So if you don't take the metamorphic grade into account, you may end up with all sorts of different alteration types that really have no bearing on the original ore forming environments. An interesting feature that we will return to here is that just below the Stolberg unit, you can actually see that this subseafloor alteration was actually overprinting earlier formed exhalites. So this is one of these iron formations that I showed you earlier, where you have basically converted into a banded garnet biotite schist. And this is what you get basically when you have a setting where the rocks basically are subsiding continuously while hydrothermal alteration is persisting. It means that the earlier precipitates that you generate on the seafloor will soon after their deposition be buried and subjected to post-depositional alteration. Just to give you a taste of some of the ore types, this is an example of this granuloblastically recrystallized texture that you find when you look into the ore. The large yellow crystals here are actually knebelite, which is a manganese-rich olivine, and which is occurring here in sphalerite and galena. The skarns at Stolberg are mainly not like the ones that you find in many skarn deposits. These skarns are more granuloblastic and irregular. So this is where sphalerite intergrown with actinolite and ferron diapside. And the feature that I alluded to earlier is that if you go into these altered rocks in the footwall, you may find silicified zones where you had stringer type copper mineralization. That is not different from what you would find below metamorphosed VMS deposit. So I should say something about the stratigraphy here, because it's quite important to understanding this kind of overprinting that I was showing you earlier, and also for the second part of my talk. So some of the key features here I've already alluded to. We have limestone at several different stratigraphic levels. If you look in the succession, it's a finding upward succession, and also that we have major pyroclastic units in the footwall of Stolberg. So what this is telling us is that we were basically in an environment that was more or less continuously subsiding. There's no big unconformity here, no big age difference. Most of these conglomerates we can attribute to local phenomena. And the interesting thing here is that the Stolberg unit here is a limestone unit which occurs on top of another limestone unit. Here's a 600-meter thick succession of rhyolitic pumiceous debris, which probably were deposited in conjunction with a major caldera forming event. So this is the stratigraphic model that we put forth in a paper in 2013, where we interpret that we had some kind of basin tumescence related to magmatism and doming, erosion of this early limestone, and then we had a major caldera forming volcanic eruption. And subsequent to that, the basin kept subsiding, and we had like a prograde evolution of hydrothermal activity, starting with exhalative mineralization and ending with the overprinting of this early exhalative mineralization and limestone by sulfides and further iron oxides. When it comes to the precipitation mechanism, if we acknowledge the features that are similar to VMS deposits, we can infer that we most likely had acid hydrothermal fluids. We see breakdown of feldspars to cerussite and chlorite. And normally in a VMS deposit, you tend to get the sulfide precipitation due to cooling as the fluid enters the seafloor. But in this case, we can actually say, I mean, if we had limestone horizons en route to the seafloor, we can actually supersede these precipitation mechanisms. And this is being shown here by these formulas for the solubility of sphalerite, for example. Now, by having this fluid interacting with carbonate, we would actually shift this fluid from the solubility window for lead zinc transport to the conditions during which sphalerite and galena are insoluble. So from this point of view, these deposits are quite straightforward to understand just by carbonate interaction. Now, this kind of deposit that we're showing you, they are not the only types of seafloor deposit that we have in the district. We also have this SAS deposit, which are stratiform deposits. And next, I'm going to talk a little bit about why they're not included in this category, why we think they are different. Well, first of all, they differ a lot in the geometry of these deposits because they are far more laterally extensive. And basically, you can treat these deposits as lithostratigraphic units, like the massive sulfide units. They occur as beds, basically, in the stratigraphic succession, which is commonly layer cake. Another feature is that they tend to occur on top of carbonate units, not within them. And if you look in the carbonate units, we have nickel and cobalt mineralization, or nickel and cobalt enriched copper mineralization. Another difference is that we barely find any phyllosilicate alteration. Instead, we find that alteration was mainly generating feldspar. And the biggest deposit in this group is a Zinkgruvan deposit, which occur in the southern part of Bergslagen. So at Zinkgruvan, we have the deposit occurring at the top of the volcanic succession, actually above it. And below it, we have a generally fining upward succession. We have a continental, fluvial, sedimentary rocks below it, and then we have a thick volcanic succession. And then in the hanging wall, we have a thick unit of migmatized pelitic rocks. So some of the key features that I want to emphasize here is that when you look at this on this scale, you may easily say that Zinkgruvan occurs at the contact between volcanic rocks and sedimentary rocks. But if you zoom in detail, you will see that it's actually a fairly thick limestone unit between the volcanic rocks and the Stratiform zinc silver mineralization. And this is immediately indicating that this is not a deposit that formed at the end of a volcanic cycle. It actually formed after these volcanic rocks have been buried and basically on top of a sedimentary succession. What is interesting about this succession is that it's zoned with regards to redox. So if you go deep into the stratigraphy, we have oxidized rocks. These are, for example, red stained metavolcanic rocks in the footwall of Zinkgruvan, or actually the regional footwall. Whereas if you go in the hanging wall, we have graphite-bearing migmatites. And this is basically the samples arranged according to this stratigraphic column, showing this redox profile, where we have Zinkgruvan basically occurring at the minimum, where we have the most reduced facies. As for the Zinkgruvan deposit, this is being shown here in red. I won't go into details about the complicated structure here, but this is the ore horizon. And this is the stratigraphic hanging wall. This is the footwall. And this is this carbonate unit, which occurs in the upper part of the footwall. When it comes to mineralization styles, this is the Stratiform zinc silver deposit. It's really mineralogically simple, mainly just sphalerite galena, with a gang of K feldspar, mainly quartz, and some biotite, locally also diapside. And then in the marble unit below, we have a polymetallic cobalt mineralization with cobalt and nickel. And if you compare these two deposit types, you can see that we have 65 million tons of mineralization on top of the marble and 6 million tons of low-grade or fairly low-grade mineralization in the upper part of the footwall. So I mean, what I want to emphasize here is that most of the ore at Zinkgruvan formed on top of the marble, not within the marble. This is the key difference from this deposit I just been talking about. Another key difference is the footwall alteration. And this is showing this huge unit here of intensely K feldspar altered volcanic rocks that occur in the stratigraphic footwall. And these are samples. And what's interesting here is that this redox front that I was alluding to earlier on a regional scale, you can actually see this in this alteration zone as well. So if you move deep into this zone, we have red stained rocks that are rich in hematite. We may find tourmaline, for example. I mean, when we approach the ore zone, we find more gray reduced rocks. So we have this zonation from oxidized to reduced facies also in the alteration envelope. These K feldspar altered rocks, they are highly unusual. They are not like the ones I was showing you in Stålberg. So when you take the Stålberg alkali altered rocks, you mainly move in the field that you can generate just by replacing one feldspar by the other. So we seldom get more than 60% feldspar in the rock. Whereas these rocks that we have at Zinkgruvan, we start to approach the theoretical maximum of microclines. So it's not unusual that we have more than 10 weight % potassium dioxide in these rocks. They are intensely potassic altered. When it comes to trying to say something about the hydrothermal fluid composition here, one of the key differences here from Stålberg, for example, is that they were presumably oxidized, based on the fact that we have an oxidized footwall succession. We also see oxidized rocks deeper in the alteration envelope. Another key feature is that the fluids cannot really have been acid because they have been traveling across the limestone units without precipitating metals. So in order to make this happen, the easiest situation would be that we had near neutral fluids that could transport metals because they were in an oxidized state. And this is something that has been shown by Dave Cook and others in a paper dealing with metal transport in sediment hosted environments. So in this kind of systems, you can basically facilitate metal transport. And what you need to have in order to get metal precipitation here is you need to take this into a redox trap, such as, for example, an anoxic basin on the seafloor, or have this fluid interacts with reductants. And this is the model that we basically derived at here for Zinkgruvan. We can show that we had an anoxic environment at this time when this basin was developing. This was the post-volcanic succession in Bergslagen. We went into a period of long-lived anoxia. And this is basically showing the expulsion of oxidized saline brines into an anoxic environment. And as stated before, most of the mineralization did not form in the marble. We had this polymetallic copper mineralization here, but the majority of the mineralization instead formed on top of the marble. So a key difference here from Stolberg is basically that we can infer different fluid types. One more like what you find in some sedimentary systems and at Zinkgruvan, whereas at Stolberg we had fluids that are more akin to what you find in VMS deposits. So far so good. We can regard them as two different facets of seafloor mineralization, but what about the skarns? When we look at Zinkgruvan rocks, we do find calcsilicates. The key thing here is that when we look in detail at these calcsilicates, we find that most of them actually can be shown to have formed after the earliest sulfide mineralization. So this is, for example, a Hedenberg crystal from Stolberg with inclusions of arsenopyrite porphyroblast, not just arsenopyrite, but actual metamorphic porphyroblast of arsenopyrite being included by Hedenbergite. This is a succession of banded skarns from Zinkgruvan. And if you consider that you have a succession of volcanic ash, limestone, hydrothermal precipitates, you basically have all the components in there that you need to form calcsilicates just by metamorphosing it. So for these kind of rocks, we don't really need to invoke any metasemantic model. We can explain them just by, you could say, like as reaction skarns, as we call them in Sweden, that you form when you metamorphose hybrid rocks. So so far so good, but for the final part of my talk, I'm going to talk about some we cannot easily explain in this way. And to do that, I'm going to venture to another area. Now I'm actually going back to one of the Svals areas. And this is the Garpenberg area, which is the home of one of the biggest zinc-lead silver deposits in Europe, which is being mined from this carbonate unit up here. Similar to Stolberg here, we have subsea floor replacement of this carbonate unit by massive sulfide ore bodies that are currently being mined by Boliden Mineral. On this side, we have the stratigraphic footwall, which is affected by hydrothermal alteration, similar to what we have in Stolberg. Whereas on this side, we have the hanging wall, which is showing considerably less alteration. So again, we have the same kind of alteration symmetry, intense in the footwall, weak in the hanging wall. But I'm not going to talk that much about Garpenberg today. I'm going to emphasize instead some of the intrusive rocks that we see around Garpenberg. So in orange here, we have dacite porphyry intrusions that can be shown that they must have intruded either in conjunction with ore formation or directly after it. Because these dacite porphyry intrusions, they truncate the altered rocks. What is interesting with these dacite porphyry intrusions is that they are chemically identical to the marginal phase of this granitoid or granodiorite granite batholith, which occurs west of Bergslagen, which I will from now on refer to the GDG. And the GDG plutons, they crosscut all of the rocks. So basically we have a transition here from forming the volcanic succession to intruding it by the upper parts of this magmatic plumbing system to finally the deeper part of the magmatic plumbing system truncating all of the rocks. And what is interesting here to note is that besides these massive sulfide deposits, we have a considerable amount of iron oxide deposits occurring proximal to these intrusive contacts. The GDG contact here, but also along some of these porphyry intrusions. And if we go close to them, we find some really fascinating phenomena. So here, for example, we have a skarnoid, which is being formed by alteration of an earlier iron formation. So we can see here a skarn of androdite and grossular and the retrograde epidote, which is mimicking and replacing a buried iron formation in the succession. So this used to be an iron-rich exhalite formed on the seafloor. Then it was buried a couple of kilometers, and in the contact aureole of this GDG batholith, it was converted into a skarnoid. And for those of you who don't know what a skarnoid is, this is basically a skarn where you can say that most of the composition of the skarn is inherited from the precursor. So for my PhD, I did some sampling of these units in detail, trying to see what was actually happening in these rocks in the process of alteration. And what we find here is that actually some of the components in these rocks are being added. For example, we have addition of the alkalis, manganese, arsenic, but we also have loss of some components, such as copper and zinc in this case, and which is really interesting to consider. Where did this zinc and this copper go? So what we're looking at here is basically the core of one of these intrusive systems that occurred beneath a Svalst type deposit at Garpenberg. And we see magmatic hydrothermal, or we could say like intrusion related hydrothermal activity, which is depleting these rocks of copper and zinc. So basically we are seeing recycling of exhalative components that can be regarded as some kind of pre-enrichment in this stratigraphic succession. So we don't know what kind of fluids were driving this. Was it evaporitic brines, like the ones that we infer for Zinkgruvan, or was it magmatic hydrothermal fluids? This is something we cannot really know, because we cannot really work with fluid inclusions in these. So we can work with fluid inclusions, but it will be difficult to know if the fluid inclusions are giving us reliable data on the processes that occurred 1.89 billion years ago. Yep. What was that? Oh, okay, no worries. So, but besides these skarnoids, we also have some like bona fide skarn deposits, such as the Smältarmossen deposit, which occur up here. So this deposit formed in the same part of the succession as the Garpenberg unit, maybe even replacing the same marble unit as the sulfide deposit we're forming in. And as Smältarmossen, we have a dacite porphyry intrusion intruding into this limestone unit and basically cannibalizing it, and replacing the limestone xenoliths here with magnetite. And in the marginal zone, we have this network of apophyses of dacite porphyry. And most of the skarn in this deposit actually formed by replacement of the dacite porphyry, not by the limestone. And this is something that we can show by looking at the textual evidence in the skarn. So we can see, for example, here skarns of amphibole and epidote, but also of garnet and pyroxene, replacing the dacite porphyry and mimicking the texture. And in these skarns, we find evidence of substantial mass gain, and also we have addition of some of the components that we were losing in the deeper part of the system that I was just showing, where we were forming the skarnoids. So this is, of course, adding a little bit of an interesting twist on the Garpenberg deposit, is that you can say what we have here is a Svalst type deposit, where we can see that the post or dacite porphyry intrusions related to Garpenberg deposits were themselves causative intrusions for forming metasomatic skarns. And when we look into these skarns, they look really different than the ones that we find at Stolberg. These actually have all the components that you would like to find in any kind of metasomatic skarn system, such as, for example, evidence of multiple phases of garnet growth, contrasting compositions, evidence of open space infilling, or evidence of selective retrograde replacement of some parts of these skarns. So like here, for example, with the androdite garnet has been replaced selectively by calcite. So we do have contact metasomatic skarns in the Bergslagen district. The problem we are having, though, is getting reliable criteria for telling the real contact metasomatic skarn apart from the skarns that we're forming just by metamorphism of rocks that were already altered. That is the problem. When did this happen? This was one of the key questions I have for my PhD. And what we did here was that we sampled all of these rocks. We basically sampled rocks showing a range from the oldest volcanic rocks to rocks that post-date Garpenberg sulfide mineralization, to the GDG intrusion, which is co-magmatic with the dacite porphyries. And the conclusion here was that we can't really differentiate between these rocks in terms of uranium, lead, zircon, SIMS ages. Within error of around 3 to 4 million years, they all yield the same age, which is basically telling us that within a few million years, we must have been building this stratigraphy, intruding it by these porphyries and subsiding it into the plutonic realm. And this, again, is something that is underlining this extreme extensional environment that we were in Bergslagen. And actually, this unit that occurs in the hanging wall of Garpenberg has been interpreted as a at least 500 meter thick caldera fill deposit. So one key question here is that, are we dealing here with a continuum, or are we dealing with some kind of overprint? So relating back to the original model that we were showing in 96, one of the features that is not really represented in this model is what is going on at depth here. And another feature that we don't really see here is the aspect of time. So this is just showing one snippet of this model, but you have to remember that according to the stratigraphic evidence, we had continuous subsidence of these rocks. So the rocks that were being formed here were subsiding while magmatic activity persisted. So if you take a single time frame here, we can speak of a continuum from a subsea floor environment here, where we had exhalative facies forming and subsea floor sulfide deposits, to a metasomatic realm down here, where we have contact metasomatic deposits. But what we don't know is that if this is really a continuum, or is it actually two different systems. Could it be, for example, that the intrusions that were forming skarn deposits down here were driving hydrothermal convection of modified seawater up here? Or are we dealing more like in a scenario with porphyry deposits and epithermal deposits, that we had like a continuum where basically fluids generated down here were traveling upwards and changing their character due to mixing with other fluids and fluid rock interaction? This is something we don't know, but we see this relationship over and over again. Another key feature here, which is maybe something I should say a difference from porphyry epithermal system, is that we don't see any evidence really of telescoping. So we don't see, for example, good examples of skarn deposits being overprinted by seawater. And the reason for this is probably that we were not in a scenario where we were emplacing a pluton and then basically cooling and collapsing the hydrothermal system. What we are seeing is more evidence that we had prograde heating of the system. A key thing here for exploration when it comes to these Svalstad deposits is that these limestone units that were being formed here in a shallow marine environment by stromatolite growth, they could become traps to mineralization at any stage during the burial history, starting from the subsea floor environment to up here to the contact metasomatic realm down here. So from a trap point of view, they're relatively straightforward deposits, but when it comes to actually understanding the succession of mineralizing events in the deposit, they are far more complicated. So this is almost the final slide, but I'm developing further on this continuum. One thing that is interesting about these so-called GDG intrusions, these are the intrusions that were co-magmatic with parts of the volcanic succession up here, is that they outlasted the volcanic succession. So when we had the transition from volcanism to post-volcanic sedimentation and formation of Zinkgruvan, we still actually had GDG plutonism at depth. So this means that this environment that we were generating here, this succession, were being continuously intruded by plutons until 1.87. And at any time during this succession, we could presumably form contact metasomatic skarn deposits. So my concluding remarks here about Bergslagen is that we have two different types of seafloor mineralization which formed at around 1.89. We have this VMS-like deposit like Stolberg, which likely involved convecting modified seawater, which either exhaled or replaced carbonate interbeds below the seafloor. Then we have this stratiform zinc-clad silver deposit like Zinkgruvan, which we believe formed by reduction from oxidized brines, which were likely sourced from evaporation of seawater, and which in many respects have similarities to sedimentose zinc and copper deposits, except for, of course, that they occur above a substrate of volcanic rocks. And then the other critical point is that we see a transition to a contact metasomatic regime at several different scales. So we can see it with depth at any given time in the basin evolution. We can also see it that in the rocks with burial history, we see increasing amount of contact metasomatic features. And also finally, we see it regionally, that at the time when the volcanic succession was not forming anymore, we had continued GDG plutonism, and we presumably we could keep forming contact metasomatic deposit until the peak of M1 metamorphism. But the key question that we don't, that I would say is this is a key question for future research, is try to understand the true relationship between the contact metasomatic process occurring at depth and the process occurring at surface, whether or not we are dealing with a continuum within large magmatic hydrothermal systems, or if we have overprinting ratio between different types of systems. And that was my final slide. So I will now leave it for questions.
Great, thanks very much, Nils. That was wow. I mean, the geologic history that you have to cover to just even get to talk about these deposits as mineable, explorable features is remarkable. So thanks for that.